Hello, myself Nitin Patil. I am assistant professor in Department of Computer Science, IIM by Philipp University. I'll be delivering this session to understand IA32-bit assembly instruction translation to object code by making use of some experimental demonstrations. To do so, I am going to make use of the NASM assembler on Ubuntu operating system. And besides that, I would be referring to an Intel manual available on the link which is added there. Now from that manual, we are going to make use of specifically few pages with respect to the example that I'm going to demonstrate to you. So let me refer to that manual. So this is the manual that we are going to make use of. Okay, so if we go to page number 35, this page number 35 basically talks about the instruction format followed by Intel 32-bit and 64-bit operations. Now, when we deal with this particular instruction format provided by Intel, one can see over there that this instruction format is divided into 6 different parts, starting with prefixes, opcode, mod rm, SIB, displacement, and immediate. Each one of them is having a specific size mentioned in the as per the manual. OK, so to demonstrate through an example, I am going to, as we know that there are different kinds of instructions supported with varying kinds of say operands. OK, so because of the kind of different addressing modes supported by Intel. So I'm going to mainly concentrate on a particular addressing mode, register to register. Now to achieve this, we would be requiring two major fields from this whole instruction format called opcode and mod rm. Now this mod rm is divided into 3 parts. So this is a byte, mod rm byte, divided in 3 parts. One can see here mod, reg or opcode and rm. Now this mod is of 2-bit from MSB side. The next 3 bits are reserved for register and then register memory. Now, if we see how exactly this organization would be, so we have to go to say particular page which would be talking about that format. Okay, how to represent that mod rm byte. Now, as we are aware that there are different kinds of operands available. Now, as stated earlier, we are going to mainly talk about say register to register addressing mode. Now we know that Intel supports different 32-bit registers. OK, starting with EAX, ECX, EDX, EBX, ESP, EBP, ESID, and you can see the order written here. Now, as if we see the mod was meant for 2 bits, so there are 4 types of mods: 0, 0, 0, 1, 1, 0, 1, 1. Now, considering the kind of instructions that we are going to take here as a sample case, they are registered to register. So mod would be treated as 1, 1. Now, each of these registers are given numbers. So I have taken a sample code for demonstrating this. So which contains these 8 instructions. OK, add, CMP, and like 4 kinds of operand forms are taken by me with different registers. Now each of the register that we have taken here from the Intel manual, one can identify that I have used the same numbers which were added there in the manual: EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI as 3-bit positions are. Now if I see this instruction for instruction that I have taken here as a sample, all these 4, 5, whatever the instructions are, they are having register to register operations. OK, first operand is register, second operand is register. Now, as our second operand itself is a register in this case, correct? So this is R32, correct? Now, if I talk about this particular case, what I did is I wrote this thing. Now, whenever we are talking, I wrote the order, whatever the order that I have taken there above. So they are written by me there. So when we do talk about which is source and which is destination, for this syntax, we are assuming that this is source and this is destination. So EBX is source, EX is destination, EDX is source, ECX is destination, and so on. So I have taken that 4 pairs of register order in the same order here. As we already said that it is a register to register, so I'm taking mod to be 1, 1. Now the source register is EBX. So if we see what is the number for EBX, so it is 0, 1, 1, correct? So let me maximize this. It is 0, 1, 1. So let us write that source number here. So it is 0, 1, 1. Now destination is EX. So EX number is 000. Similarly, again mod 11. Correct. Now EDX is 010. And then we have ECX as a destination 001. Similarly, ECX 001, ESI to be 110. 11. Then EDX is 010 and EDI to be 111. Now let us collect together these all bit position to form a byte. So 11011 000. Okay, second number that I'm going to write now 11010 001. Third one 11001 110. 11010 Now let us divide these 8 bits or a byte into 4 bits ultimately to convert them to hex. So now let us write this hex representation for these all binary numbers. So 8 plus 4 plus 1 13. So D, and this next number is 8. Similarly, in this case it is D1. Now 8 plus 4 12. So C, 8 plus 4 12 plus 2 14. So we will have here E. Then 8 plus 4 plus 1 13. So D, and 4 plus 2 plus 1. So 7. Now this is the mod RM byte representation for all the 7 instructions that we have written above. Okay, so let us write that representation here. So we got D8. Here we got ECX EDX. So D1. Then ESI ECX. We got CE. Then we got EDI EDX. So this is D7. Similarly, EX EBX. We have a D8. Then ECX EDX. We have D1. EDI EDX. It is D7. Correct. And ESI ECX. This is CE. Now what I'm doing is like we have from the translation point of view, we got the mod RM byte. Now we will require an opcode to be found. Now if we see all these instructions are having second operand to be registered. So it is a 32-bit register. So if we go to manual, for every instruction, manual has a table given for the opcodes. Okay. Now there are different addressing modes. That's why different opcodes can be seen for particular instruction like add say for a while. So as we know that our second register, second operand is register and which is 32-bit. So we'll go here and we'll see this R32 RM. This operand could be register or memory, but second operand should be register. That's what we are saying. So the opcode is 01. So let us write that 01 here before this D1. So it is 01 D8. Now next instruction is CMP. So let us go to page number 255. So CMP. So again find out R32. So we got R32, RM32. So opcode is 39. So let us write 39 here. Now next is move. So 687 is the page number. So let us see for move R32. So this is the case. So 89. Correct. Let us write that 89. Now all next 3 instructions are again are move with registers only. So 89 would be repeated, right, for all of them. Now we have next instruction to be OR. Now this OR we have to find out appropriately from page number 818. So 818. So let us find out R. So we got 09. This is the one. So 09. Let us write that 09 here. And last one we have sub. So sub is page number 1306. So sub again R32. So let us find out this one. Correct. So we got this here and number is 29. Correct. So let us write that 29 there. Now this is what we got the translation. Now we have to verify whether NASM generates the same thing or not. OK, so what I did is I wrote this code in a file named it with ACM. For example, ACM teach Emacs ACM teach.asm. Yeah, now you will see that I have taken the same code here. Whatever the code that we wrote, correct? In the file. When same code is written, add CMP, then move, correct? Then move, R and sub. Let us try to check when we translate this code, what exactly is shown. So let me translate this code by nasm-plf32. Now while translating, I will generate a listing file so that I can see what is the kind of translation actually applied by the translator or the assembler. So I will use this -lp.lst. This is a listing file generated. So let us try to compare the translation that we got. So first instruction was add ex, ebx. We got 01d8. We got the same thing 01d8. CMP ECX CDX 39d1. So we got 39d1. Similarly 89CE, 89d7, 89d8, 89d1. Then we had R, so that's why 09d7 and then 29C. So we successfully could get the translation for the instructions where both the operands are registered. On the similar line, we can work out with respect to other instructions also where different operand types possibly could be. And thank you very much.